So good morning, everybody. Welcome to the TST meeting. Here, we're gonna have sparse attendance today because there are a number of people are at the E4 workshop in Stanford. But we'll hold the meeting nevertheless and record it, and just simply watch Jordan's presentation. Jordan present the Atomix architecture and ONOS cluster architecture as it's been revised into separate processes. And with that, I'm just going to pass the ball to Jordan. Presenter. All right. All right, next.
All right, so I'm going to talk about the Atomix 3, which is the new release of Atomix that's coming pretty soon. The new ONOS controller architecture that I talked about a while back and how Atomix fits into that. So, quick overview. I'm going to do a little overview of the current architecture, talk about Atomix 3 and the features, and then how it fits into the new architecture that I talked about here a while back. So obviously, in the current architecture, obviously distributed primitives are a huge component of distributed systems, and ONOS, all the stores, or many of the stores use primitives to replicate changes to other nodes. And for the most part, for most of the primitives, the way these work is we have a bunch of RAF partitions. So this is a cluster of 5 ONOS nodes. And we literally just have a bunch of RAF servers just embedded inside all the ONOS nodes. And so when you use a primitive, it will reach out to other nodes, look for the partition in which data is stored, and then make calls to other ONOS nodes. But there are some problems I see with this architecture. For example, these embedded RAF partitions, RAF as a consensus algorithm has really strict constraints on cluster configuration, and ONOS, since it's embedding the RAF partitions, also gets those really strict configuration constraints. There are some performance issues that without a whole lot of benefit to actually embedding the partitions. So, for example, resource usage in the RAF partitions affects ONOS nodes and vice versa. But many times, even though we're embedding RAF partitions, you would think that we're getting a lot of benefit from these servers being in the process locally, but in reality, most calls still have to happen remotely to some other node anyways. So, for example, given like 2 ONOS nodes, if node 2 wants to make a call to some primitive, but node 1 is the leader for the partition that it's trying to operate on, it still has to make a remote call to node 1 and to perform some operation. So. The vast majority of the time, there's not a whole lot of benefit to actually embedding the RAF partitions. Some additional problems. One of the problems we ran into in ISSU was that it becomes really difficult to manage the RAF logs during upgrades and sort of a buggy process. And then when we want to introduce new features into the RAF partitions, there's like a chicken and egg problem where in order to be using a new feature that's in a RAF partition, the entire partition has to be upgraded. But the first time an ONOS node is upgraded, it's trying to use the new features. And so that was really the original basis for this refactoring. And then there are a couple of performance issues in using RAF in general, which I'll talk about later, which are that RAF is, even with partitioning, RAF is still really limited in latency and throughput because writing to disk can require synchronous replication and things like that. And so for that reason, some users have in the past requested a faster replication protocol for primitives, which is part of this. And so our solution, which I talked about here a while back, was to re-architect the ONOS controller to move RAF partitions into a separate process.
I think it's just a caveat.
Yeah, and that gives us relaxed configuration constraints for the ONOS controller, and then we would only use in-memory replication protocols on the controller nodes. And so going back to this diagram of 5 ONOS nodes with a bunch of RAF partitions in them, all we're doing is adding a separate Atomix cluster and then moving the RAF partitions into that cluster so that ONOS controller nodes are no longer participating in the RAF instance algorithm.
Well, it basically become pure clients, right?
Yeah. There is another component to this, but we'll get to it later. Oh yeah, and so the benefits of this are that, like I said, we isolate the ONOS and Atomix processes from each other, so they're not. So one process going downhill doesn't affect the other, and vice versa. We can upgrade. The big thing for ISSU is we can upgrade Atomix and ONOS independently. So looking at this chart, we can upgrade Atomix. We can upgrade an entire Atomix cluster to introduce all the features, all the new features before any ONOS nodes are upgraded, and that allows the first ONOS node that's upgraded to begin using those features. And it really simplifies a lot of the coding and required by ISSU. And then, yeah, like I said, we relax the configuration constraints of the ONOS controller just by the fact that they're no longer participating in that. So Atomix 3. So how does the new Atomix release fit into this? So this release, it's really been in development since last summer when I started. First I re-architected the RAF implementation to fix lots of architectural issues. It's now way more stable than it was then. And then the second sort of step to this was moving a lot of the distributed systems components of ONOS into Atomix. For instance, messaging, cluster management, primitives, etc. And the reason for doing this is because ONOS isn't really a distributed systems project. It's an SDN controller, so those components can be better maintained elsewhere, and that's what this rationale sort of says. So, yeah, moving all the primitives out into a separate project encapsulates those distributed systems primitives in another project, and then Atomix users benefit from the work that's been done in ONOS, and conversely, ONOS users benefit from all the work that gets done in Atomix. And the argument that I made last time when I first proposed this was that the core ONOS distributed systems components would get a lot more users and a lot more testing. And I've already seen that becoming coming to fruition a lot more quickly than I thought it would. Atomix has a bunch of new users and has several new regular contributors that we would have never gotten had those components remained in ONOS.
Cool.
There are more people working for free on the core ONOS distributed systems components.
Awesome.
So the features. So I'm going to do a little overview of the features in Atomix and then talk about how they fit into the new ONOS controller architecture. So some of these features are really similar to what we have now in ONOS with some minor changes because of some of the relaxed constraints. So the cluster management in Atomix now looks a lot like it does in ONOS, except we're able to do like really truly dynamic cluster membership, node discovery, and things like that because not all nodes are necessarily RAF nodes, which relaxes those constraints. And then there's like replication of member metadata. We still use FireCruel for failure detection. And so this is what setting up an Atomix cluster looks like. This is showing an Atomix instance being configured with a local member, enabling multicast, and then these partition groups I'll get to in a bit. And so this is just showing that it looks really similar to what we have in ONOS now. This is getting an instance of the cluster membership service and listening for nodes to be added and removed. Similarly, messaging looks pretty similar. I moved the low-level netty messaging implementation into Atomix, and then there's a higher-level topic-based point-to-point communication API, which is still called Cluster Communication Service, which looks very similar to what we have in ONOS. There is an addition of a new messaging abstraction, which is it's basically a pub sub messaging abstraction, which I'll show an example of later. Yeah. So yeah, this is the communication service, which looks really similar to in ONOS. You got a subscriber, give it a subject to subscribe to, and then to send a message to another node, you get an instance of a member, send it to the member ID. So what the event service, which is the pub sub abstraction, does is removes the need to have a member ID. So when a subscriber subscribes, it replicates subscriptions using a gossip protocol internally to other nodes, and then so all you then do is send a message to a topic, and internally Atomix will dispatch it in a round robin fashion. So this is sort of what it looks like. A publisher publishes to a topic, it gets dispatched to some subscriber round robin like that. And I actually got this from, I used to work on a project called Vertex, which has a core, they call it the event bus, which basically works like this. And it's really cool because it, obviously, for obvious reasons, it separates from producers from consumers. Yeah, and so primitives. So obviously, like I said, primitives are a core component of ONOS. They've also been a core component of Atomix. That was what the original project was, were RAF primitives. And so these, of course, still remain. Except there's some refactoring done to it. So now primitives are just replicated state machines. And the state machine abstraction in Atomix 3 is now protocol agnostic, so it's not specific to Raft anymore. The client API for primitives is a lot nicer. It uses Java proxies to call methods on state machines, so they're a lot simpler to implement. There's actually a REST API now, so primitives can implement a custom REST API. And what this allows is when we have an external Atomix cluster, we can also use the REST API to inspect the state of the cluster, which is cool. And then, of course, like I said, custom primitives are a lot easier to implement. And so the primitives, I ported basically all the primitives that we use in ONOS over to Atomix, and so these are what they look like, and these are not surprising. And yeah, also the API for building primitives looks really similar. So this is using an Atomix instance to get a consistent map builder, setting some options, building the map, and then calling some methods on it. Another example of a distributed lock. So the API is a lot more consistent now in Atomix, where every builder builds a synchronous version of the primitive, and then there's an async method to get the asynchronous implementation. So every primitive implementation, every synchronous primitive has an asynchronous implementation that can be gotten like that, and you can also do the opposite direction. So now this is where we get into new things that are not surprising to ONOS developers. So, I mean, originally Atomix was basically a Raft implementation, and just after seeing all the stores in ONOS and lots of instances of a primary backup protocol in ONOS that's not really abstracted that could be, I set out to generalize more than one state machine replication protocol. And so that's what this is. So Atomix now has several replication protocols that can be used to manage primitive state machines. So obviously RAF we've had for a long time. It works, I mean, it's basically log replication. Alexa leader replicates logs to followers, and then a primitive is an in-memory state machine that is basically a replay of the RAF log. So the new protocol is a primary backup protocol, which at a high level looks sort of similar to RAF, but it's in memory only, so it has tons of performance advantages. So RAF, a lot of the performance deficiencies of RAF come from its need to be consistent, because that's its purpose. So it has to do synchronous replication, has to write things to disk. The primary backup protocol has a lot fewer constraints, so we can replicate changes asynchronously, replicate changes synchronously, only hold changes in memory. And so the way the primary backup protocol works is if there's a raft partition in the cluster available, it'll use the raft to elect the leader, which still gives its strong consistency in terms of leader election. But because we have more control over the primary backup algorithm, we can also do things like rack awareness, which is cool. And so, yeah, both of these protocols are pretty similar. Raft, like I said, you elect a leader, replicates followers. Some client sends operations to the leader replicates them, the leader applies them to a state machine, and then responds. And we can just as easily replace this image with leader and follower with primary and backup like this. And so because these two protocols are really similar, we can it was really easy to replicate primitives on both of them. So to the configuration of Atomix. So in order to manage these various protocols, there's a new abstraction called partition groups. So partition groups are basically sets of partitions that implement a specific protocol. And so an Atomix instance or an Atomix cluster is configured with several partition groups, and the partition groups define which partitions are in the cluster and which protocols they implement. And there's one required partition group, which Atomix uses for, it's called the management group. Atomix uses it for primary elections, for storing primitive information, so you can read information about where all the primitives are stored and things like that. And then to manage transactions. And aside from that, users can configure additional partition groups wherever they want, based on how they want to store primitives. So this is back to the Atomix instance configuration. So this is showing a raft management group being set up, which this is the partition group that Atomix will use to like I said, store transactions, store primitive information, things like that. And then this is also configuring a raft data group, which can store primitives in this group. And they just have a name, which you can use to indicate where a primitive is stored. And then a primary backup partition group with 32 partitions. And Atomix also has a configuration file format. This is OCON, where you can configure the partition groups as well. Yeah. So what the cool thing that this gives you is you can actually now split the cluster into several parts. So you can have raft partitions on one set of nodes and primary backup partitions on another set of nodes, which this becomes important for the ONOS architecture. And they can also overlap. I mean, essentially, when a node is started, it defines the partition groups that it participates in, and that's it. And so the way that you use these partition groups, or the way that you tell a primitive where and how it's stored, is by using a protocol configuration. So the protocol configuration, basically, when you construct a primitive, you tell it the type of protocol to use and the group in which to store the primitive. And the protocol configuration has some other protocol-specific configurations, like in primary backup has a replica count, and raft has consistency and thread models. You can define the timeout for the primitive, the retries to use for the protocol, and things like that. So this is what it looks like. This is a consistent map being constructed to use the multi-raft protocol, which is just to use a raft partition group. So first, this constructs a multi-raft protocol instance with linearizable consistency, tells it to communicate with the leader, and then configures the map to use the raft protocol. And you can also pass in the builder, you can pass a partition group name to store the primitive node. And just like before, you can also do this in the OCON format or JSON. And so what this will mean is, given the test primitive, Atomix will know that it's supposed to be stored in raft partitions, and it will just provide those partitions to the primitive. Similarly, this is the multi-primary protocol. This is constructing a multi-primary protocol instance with 2 backups for the primitive, so you can assign different backup counts for different instances of a primitive. Yeah, and then so this is just creating a consistent map that's replicated using the multi-primary protocol. Similarly, the configuration file, and just like before, this is telling Atomix to store the primitive and primary backup partitions. So how does this fit into the new cluster architecture that I talked about a while back? So given all these features, there's a little addition to the ONOS controller architecture. So we have a 5-node ONOS cluster. We add, say, a 3-node Atomix cluster, push raft partitions into the Atomix cluster. In addition to that, the new architecture has primary backup partitions on the ONOS controller nodes, and there's a reason for doing this. Yeah, and so but first, what this gives you is an external Atomix cluster. So in the external Atomix cluster, we have the raft system partition group, which is used for primary elections and things like that. A raft primitive group, which we use for storing the raft primitives, and then on the ONOS controller nodes, there are also Atomix instances embedded, and they use the primary backup partition groups. And this doesn't hurt any of the configuration requirements because primary backup doesn't have the same sorts of constraints that a consensus algorithm does. And then in the implementation, we just wrap all the Atomix primitives are really similar to the ONOS primitives now, so rather than breaking the ONOS API, we just create wrappers from the ONOS primitive APIs to Atomix APIs. And then we can support, like some users have requested in the past, either using the raft protocol or the primary backup protocol. So the cool thing that we get from the primary backup protocol existing on the controller nodes is, say in this architecture we get a device, and we can map the device to a partition, say this green partition, and this node down here is the primary for that partition. Well, we can just use the primary election to map the device's master also to that node. And what that gives us is when this node uses primitives keyed by the device ID, it's always doing writes and reads locally, which is how a lot of the stores in ONOS are currently designed. But so what this allows is for us to potentially push a lot more of that logic into primitives, where it can be reused, and obviously we can benefit from general improvements to primitives. And I mean, this is basically pushing a very common pattern in ONOS into primitives, which is sort of a long-term goal. So the status of this. So I've been working for the last couple of weeks on implementing this new architecture, and just at the end of last week, I got it all working. So on the test cells, so you can now I updated scripts to deploy an Atomix cluster, standalone Atomix cluster, replaced all the primitives, and ONOS now uses Atomix for cluster management, for messaging. And then it creates a primary backup partition group and communicates with external raft partitions. There's just a lot of cleanup to do around our test infrastructure and things like that. And then I have to get an Atomix release out of it. That's mostly it. And then if you're curious, you can go to the Atomix stuff. So there's an Atomix website, Atomix Google group, and the GitHub repo.
Well, this is excellent work. It's great. Do let me or let us know what kind of cleanup we can do, with the test infrastructure. I know that you and I talked about potentially augmenting the warden to allow creating separate physical nodes for the Atomix.
Yeah, that's the biggest thing right now. So the way I have it set up currently is, basically when it gets a cell, it just deploys the Atomix processes in all the nodes in the cell next to the ONOS processes. So it will just deploy the Atomix processes first and the ONOS processes.
Do you need, is there any special requirements for, if, let's say we do set up a new sort of a type of a node, is that node system-wise or software-wise, can it be the same as the base
Yeah, I think
ONOS
it's
node?
the same. It's
Okay.
worked fine
Okay.
now.
So we just created it, but it still would be good to create in a separate sort of separate not processes but containers.
Yeah, I think so.
Okay. So I should be able to come to that. There will still probably be, at least on the shared cells, there will still be a limitation of 10 nodes per slot, which means one network node and up to 9 nodes. Is that gonna be okay for us, most testing, or do we need to
No, I think
do we need to?
I'm trying to think. I think it's fine. I mean, so the max you can get is what? Let's see.
Would be 5 and 3 and
yeah,
network.
5 and 3. Yeah.
Because there's possibilities we could do, and we can discuss those offline. We don't need to probably take this meeting for it. For potentially merging 2 slots, effectively could go much higher.
Sure,
So
yeah.
we can discuss that. But again, this is excellent work, Jordan. I really like this.
Yeah. I'm really glad that you're seeing already people more interested in
I was
using
actually
stuff. That's cool.
I was actually surprised about that. I've been surprised about how many people have gotten interested, and I've given people commit access to the Atomix repo, and they've been. It's kind of funny. It's kind of a funny phenomenon when you give someone commit access. Some people just sort of run with it. It takes time to work. I was actually surprised at that.
That's cool.
In terms of, you mentioned that there will be, currently that there are wrappers for the existing ONOS primitives, which have been the gut of them now moved to Atomix. Do you want to approach that as a long-term approach, or should we deprecate these and then encourage people to, for future, we sort of not breaking the API, but encouraging people to draw stuff straight from the Atomix.
This was actually something that I've been wondering. I've been going back and forth on for a while. I don't have any strong opinions on it. Yeah, I mean we could deprecate the primitive APIs now.
That would be my inclination, and simply the reason is just reducing the number of objects, simplifying the system.
Sure.
Unless there is a need, unless we sort of envision that layer of the ONOS primitives would potentially house some other distinctive behaviors, but to me that seems almost counterproductive.
Right. Yeah. So anything that can be in that layer.
Exactly. It's in theory should be in the distributed systems part. So I think what we probably ought to do is just deprecate them.
Yeah.
I mean, again, that can be done in phases, right? It doesn't have to be done now. It's just as part of the cleanup, I would deprecate them, and then future stores can be just drawing on the Atomix primitives.
Yeah, I guess there's not. It makes a lot of sense because you're just maintaining wrappers in this. Really.
Yes. But I think it's a good approach as an intermediate step, right? Because that way you can't break things. This is great. Any comments? So one more quick question. So a lot of this, I know that you've been doing also a lot of work on Atomix 2 branch, right? So a lot of these things have some of these things been backported? I mean, clearly not the separate cluster stuff, but the primitives and things like that.
So the versioning has been sort of weird because my first thing was, like I said last summer, refactoring the Raft implementation to fix architectural issues. And that became Atomix 2. And then I started building Atomix 2.1 with all the primitives, but it's sort of weird how the versioning has been. That's the only reason that I bumped the version to 3.
I think that's good. Numbers are cheap.
Just because users were like, can I use Atomix 2 primitives? But because there have been releases of that for the Raft implementation.
Yeah, this makes a nice clean start.
But but as far as ongoing work for the last couple versions of ONOS, I've generally been doing work directly on the RAF implementation in the 2.0 branch, and then cherry picking that ahead into the new work, so that I can make sure that and I've stayed pretty consistent with ensuring all the changes from our ongoing work to fix bugs and things get into this, so it should be a pretty smooth transition.
So is this now, at least on a site, is that under review or is that already been merged?
No, I haven't. So I haven't released. I just have to do an Atomix release. Currently, it's just using snapshots, so I haven't done the release yet. I'm probably gonna do it this week. Just waiting for a couple pull requests to get merged.
That's excellent.
And then, once there's a release, I'll be able to configure the bug stuff correctly.
Yeah, this is awesome. Any other comments from? Oh, I think we still have only John online, right? Yeah. I think this was excellent presentation. I think probably can work also for Atomix users, right?
Yeah, actually, that's what I plan to do. I plan to post this on the Atomic stuff because the website is a work in progress, so a lot of people have questions about this exact stuff.
Mm-hmm. Yeah, this is a lot of great material. I mean, I don't have any other questions. Anybody else? Other than, again, saying this is great work, and thanks a lot, Jordan. All right, with that, I think we're gonna close the meeting. See you in 2 weeks, everybody. We also got one more thing before we depart here. We're probably nearing the time where different projects may need to start doing presentations for their many milestones. So we may actually schedule meetings more frequently in order to be able to fit some of those presentations in. So anyway, that's all I had to add. Goodbye, everybody.